Good afternoon, everybody. Let's get started with the class. For announcements, you have a homework due tomorrow, so that's an unusual day, so I want to call it out. Tomorrow, 3:18, 4:40 p.m., so take a look at that homework's due. If you have any questions on that, stop by office hours. We also have an exam this week on Wednesday, 3:19 during the regular class period. So it's going to be the regular class period plus 30 minutes grace period to submit your exam if you need some extra time to get that exam uploaded to Canvas. The material will be capacitors and inductors through transistors. And so you can see the announcement that I sent out via Canvas today, and that lists the topics and the rules that will be printed on the front of the exam and some other information there. So you can see the review problems and the practice problems. Those are separate sets. And you should be able to see that assignment listed with a start time and a due time on Canvas now. So you can take a look at that in case you've had a couple of people had to have an alternate exam time. So if you have an alternate exam time assigned already, you should see those times listed on Canvas for that assignment. So my office hours will be right after class for any questions you might have. So stop on by and just stick on this Zoom session after class. Okay, so what I wanted to continue with was the discussion of transistors and transistor circuits. So we're going to go back to the whiteboard and talk about a pretty common type of circuit. So last time I diagrammed a circuit. We worked through a circuit where I showed a transistor in the different regions of operation, the cutoff region, the linear region, and the saturation region. And I mentioned that in that circuit, you can operate basically that circuit as an amplifier in the linear region or as an electronically controlled switch in the saturation or cutoff region. So what I'm going to work through today to start is an example of using a transistor as an electronically controlled switch. Sure, transistor as a switch. So why might you want one of these? Let's suppose you have a microcontroller that's controlling some kind of load, like a motor or a light or a heater or something like that. Oftentimes, so we haven't talked about microcontrollers yet, but microcontrollers can output a voltage like 0 volts or 5 volts, and they cannot supply a lot of power, but they can supply a range of, or let's say 2 voltages that are a digital signal. And so you couldn't power a motor or power a heater with the output of a microcontroller, but you could put a switch between a microcontroller and a heater, a motor, something like that, and then use the microcontroller to control the switch to control the current to a motor or whatever your load is. So that's what we're talking about today. Let's suppose we have a circuit that looks like this. Okay. So what I'm going to do is have this resistor and diode be the load. So I want to control current from a source. Let's say this is a 5-volt source up here. Remember, when I list a node voltage next to a node, next to a terminal like this, it means there's essentially a power supply connected between ground somewhere in the circuit and that node to supply power to something. Okay. And then I'm going to come here and I'm going to put a transistor. And that transistor is going to control the current through the diode and resistor. So this transistor can either allow current to flow or stop that current. And let's suppose this diode D1 is an LED. So D1 is an LED, and it has a forward voltage V sub F of 1.8 volts. Okay, that's So that's not 0.7 volts. This is not a silicon diode. This is an LED. They have different forward voltages. But let's say when you have something like 25 milliamps running through this diode, the forward voltage is 1.8 volts. Okay, let's suppose this transistor, this is going to be transistor Q1. So Q1 um, is a silicon transistor, and let's suppose it has a beta value of 100, just to make the math simple. It's around a typical value. And let's suppose that when this transistor is saturated, the collector to emitter voltage is 0.2 volts, like we've been assuming. So VCE sat is, let's say it's 0.2 volts. And let's say that when you have current running from base to emitter, remember that looks like a diode junction between base and emitter, VBE equals 0.7 volts, looks like a silicon diode, when IB, the base current, is greater than 0. That means just when base current is flowing. Okay. Okay, so someone asks in the chat, are you able to explain the reasoning behind the symbol of the transistor? Specifically, why does the transistor have the dash branching off of it? Let's see. I don't know what the dash is, but let me say this. So this is just the transistor symbol. It represents the terminals of the transistor, the collector, the emitter, right, and the base. And it's just the symbol we use. If you have a PNP transistor, the arrow goes out. If you have an if you have an NPN transistor, the arrow goes out in the emitter. If you have a PNP transistor, the arrow goes in. If you have a FET, a field effect transistor, like a MOSFET, and there are different variants of those and different symbols. So we use the symbol to identify the type of transistor that we have in a circuit. Okay, and as to why exactly we picked this symbol, I mean, other than saying it kind of makes sense that you have um, 3 terminals and the flow of current is from collector to emitter out of that in that direction there, positive charge flow out of the emitter. I guess that's my best guess at that. Okay, so we're going to control the current here through the diode and the resistor using this transistor, and the way we control that is using base current. So if I have some terminal here with a base resistor, okay, I'm going to call that base resistor RB. Okay, and if I apply voltage here, let's call that voltage Vn. That voltage is going to cause a current to flow into the base. We're going to call that IB. The IB. And that IB will control IC. Okay. And then you have VCE between the collector and the emitter. Okay. And then let's give a value to this, or a symbol for this resistor here. We'll call it RC, collector resistor. Okay, so if you apply a voltage that's going to cause a base current to flow, which is going to cause collector current to flow. So base current causes collector current to flow. And let's suppose that we want to control this current using either 0 volts or 5 volts here at the input. So if I apply 0 volts, get no current flowing. If I apply 5 volts, that controls current through the diode. Okay. and this would be out of a 5-volt microcontroller. If you've ever used a typical Arduino microcontroller, you have 0 volts or 5 volts out of a digital port, you can control something. But let's suppose we want current, a current amount like 25 milliamps flowing through that diode. So typically you wouldn't take that much current from a microcontroller pin. Okay. So the design problem here, this example is this. How do we choose the values of the collector resistor and the base resistor? We know we have 5 volts here. We have 5 volts here. So how do we choose these resistor values such that when this transistor is saturated, right? Remember, saturated is like a closed switch for a transistor. When this transistor is saturated, how do we, what resistor do we use to get 25 milliamps, let's say, flowing through that diode? And then what base current do we need? Or alternatively, what resistor value do we need here when you apply 5 volts to be able to saturate that transistor? Okay. All right. So let me write those questions down so I can be a little more specific here. So part A, find RC, the collector resistor, so that the diode current and equivalently the collector current is 25 milliamps. IC equals 25 milliamps, not amps. When Q1 is saturated. Okay, so we got to figure out the value of that resistor there. And part B, the second part of the design, is find RB so that Q1 is saturated. That's saturated when Vn is 5 volts. Okay, apply 5 volts, saturate that transistor, have current flowing, 25 milliamps flowing. Apply 0 volts, that shuts off the current. Okay, so it's an electronically controlled switch here. All right, okay. So part A, let's figure out what that RC value has to be so that 25 milliamps flows when Q1 is saturated. Well, I'm going to write a KVL equation. Why am I going to do that? Because, so what values do I have? When current is flowing, I know the voltage across that diode. I know it's going to be 1.8 volts. When this transistor is saturated, I know VCE. I know that's going to be 0.2 volts. I could figure out what the voltage is across this resistor, right, using Ohm's law. It's going to be ICRC, right, ICRC with that polarity. Right, this is the diode voltage here, VD. This is VCE. And remember, this 5-volt node voltage up here comes from a source. If I wanted to, I could draw in this source. I could say that 5 volts is caused by a 5-volt source right there. So I think I have enough, knowing the current, knowing these other voltages, I think I have enough to solve for RC. Okay. And I think someone asks in the chat, a message to me, what's sometimes these grounds, if you remember from that one slide, sometimes you'll see these grounds drawn like this. Sometimes you'll just see them drawn like that, like a line without the triangle. You'll see this symbol. I've seen this symbol sometimes. Okay, so if you see a triangle in the homework like this, at where there would be a ground, where you think there's a ground, it's probably a ground. Okay. All right. So let's write a KVL equation. Try to solve for RC. You can start anywhere. I'm going to run a loop that goes around here, write an equation for that loop. So that would be, let's see, let's start here and go around counterclockwise. No reason, just I felt like doing that. -5 plus VD plus ICRC plus VCE equals 0. Okay. And so I can solve for ICRC because I want to solve for RC. ICRC equals 5 minus VD minus VCE. So RC equals 5 minus VD minus VCE over IC. Okay, so we know VD. VD is the forward voltage of this diode when current is flowing through it. Okay, so this is 5 minus 1.8 diode voltage, forward voltage when current is flowing. It's 1.8 volts minus VCE. Well, the transistor is saturated, so VCE saturation is 0.2 divided by IC. Well, we know we want 25 milliamps flowing through that diode equivalently into the collector. So 25 milliamps, that. Okay, so let's see, that works out to be RC equals 120 ohms. Okay. So if I saturate this transistor and I have 5 volts up here, I will have 25 milliamps flowing through that diode if I use a 120 ohm resistor RC. Now we have to figure out, well, how do I choose RB so that I get that transistor saturated, right? So I get it saturated, choose RB when I apply 5 volts to the V in node. Okay. Well, I think we can use another KVL equation here because, why do I say that? Because I want to solve for RB. This voltage here is IB RB, right? This voltage here is VBE. So I know VN is 5 volts, and remember, you can, if you want to, you can draw a source here, plus minus 5 volts, connect it to ground. That's how VN becomes 5 volts with that source. So now I know that voltage. I know we're going to figure out the current. We're going to figure out what current we need based on IC. VBE we know is 0.7 volts when current is flowing into the base. Okay. All right. So let's start out with the KVL equation to try to solve for RB. So, oops, let me start here. -5 plus IBRB plus VBE back to the starting point equals 0. So -5, that's VN, minus 5 plus IB RB, right, plus VBE equals 0. So RB equals 5 minus VBE over IB. So we know VBE, we don't know what we want for IB yet. So let's figure that out. So we want that transistor saturated, and we know that in saturation, when the transistor is saturated, that IC is less than beta IB, and I'm going to put linear. That says, let me write that again. This is the beta linear value. In other words, when this transistor is operating linearly, IC equals beta linear IB. Okay, if we use that beta value and just assume it stays constant, in saturation, even though you increase IB, IC does not increase. Okay, so IC is going to be less than beta IB. Okay, I can turn this around and say, so that means IB has to be greater than IC over beta linear. And beta linear, we're saying, is 100 here. Okay. All right, so we know IC. We know that IB has to be greater than IC, 25 milliamps, 0.25, over 100, right? And so that means IB has to be greater than 0.25 milliamps. Okay, so that's the constraint. So for a textbook problem, you can make it 0.26 milliamps or anything bigger. In lab, what I would do is think about this and say, well, what current do we really want? Do we really want 0.26 milliamps? Because if that beta changes just a little bit because of temperature, maybe the data sheet's a little off, there's usually a range of betas in a data sheet. Maybe we want to make an engineering decision that's a little conservative so that we can, make sure that this transistor is going to be saturated for some variation in beta of that transistor. Okay. So it's a judgment call. Um, you don't want to choose too little current because if beta is too low, then you won't saturate the transistor. You don't want to specify a whole lot of current here because then if this is a battery, battery powered device, then you're wasting battery energy, right? And if you if you choose too much current, then you're heating up the transistor. Why do that? So so I'm going to choose IB equal to 1 milliamp. Why 1 milliamp? Well, because I think, I'm looking at this, I don't think the beta is going to fall to 25. If I make this 25, then I would still be saturated. I'd still saturate this transistor with 1 milliamp. 1 milliamp isn't a whole lot of current, so I'm not going to heat that transistor base to emitter junction up all that much. 1 milliamp isn't much to draw off a battery. I mean, if you chose 10 milliamps, that would work, but you'd be taking battery current, right? Discharging your battery unnecessarily if this is a battery powered device. Okay, so I just chose that. So I choose as my engineering decision 1 milliamp. Okay, so now I can go back and solve for RB. RB equals 5 minus VBE, 0.7 divided by 1 milliamp. And what's that? That is 4.3 k ohms. Right? Okay. So if I use 4.3 k ohms for RB and I have the circuit and I apply 5 volts here, I will saturate this transistor if I have 120 ohms with this diode, and that will cause 25 milliamps to flow. Okay, so I now have I'm using the transistor as an electronically controlled switch. This is the electronic control here. I can apply 5 volts to turn that load on. I can apply 0 volts to turn that load off. There's nothing mechanical here. And that's how you would do this. Okay. So let's see, someone asks in the chat, I want to get back to that. How can both of those currents add at the top of the diode node and not violate KCL? Oh, okay, so let's look at the currents here. So you have current IB and IC go into here, right? So you have, let's say 25 milliamps IC. Here, coming out of the emitter, you have 25 milliamps plus 1 milliamp. So here I have, right, 25 milliamps here. This will be 26 milliamps, right? Because I have 1 milliamp going into the base, 25 coming into the collector, 26 going out. And then going this way, I have 25 milliamps and 1 milliamp. So that's how the current flow, that's how the current flows. 1 milliamp this way, 25 milliamps this way, 26 comes out of the emitter. Okay, so that's how we not violate KCL there. Someone says, is there a way we can calculate the most efficient base current? Well, you could, well, yeah, I mean, there's probably in the data sheet a minimum value of beta for the conditions under which you expect to operate. The temperature range, part-to-part variation. There's usually like a for a beta, like a typical value and then a minimum value within their specified temperature range. So you could just use the minimum value. Let's suppose the minimum value, I said, well, what if beta is 25? Then we'd need 1 milliamp. If the minimum value is like 50, then I would use 50 here and you'd get, half a milliamp instead of 1 milliamp. So that would be more efficient. Okay. Yeah, good questions. Okay. So this is what I wanted you to get out of this class, to be able to control a load electronically, because inevitably at some point in your projects, you're going to run into a microcontroller where you want to control some kind of load. You can use a BJT bipolar junction transistor for currents on the order of, 100 milliamps, maybe a couple hundred milliamps. I've seen them work up to 500 milliamps. If you're controlling larger currents like multiple amps, 5 amps, 10 amps, 20 amps for, let's say, a larger motor, you probably want to use a field effect transistor here. We're not going to talk about that in this class, but given this kind of setup of the circuit, seeing how to control current uh, between a load and ground, you could you could probably pick this up on the web, learn how to use field effect transistors like MOSFETs. And also the next class that I teach in the fall teaches how to use MOSFETs and all about those. And we dig in, it's a couple lectures on that. So can't fit it into this class, but I wanted to show you this concept of transistors as switches. Okay. All right. So we've hit another milestone in the course. Let me bring up a slide here. All right. So here's where we are in the class. I like to bring our roadmap up every once in a while. Um, so we went through the circuits part of the class, basic theory. This is a volt, this is an amp, this is a watt. We talked about KVL, KCL for DC circuits. We talked about transient circuit analysis, right? The exponential decay and rise of voltages and currents in first order circuits. We talked about analysis of AC circuits, phasors, and impedance. We talked about semiconductors. We talked about diodes and transistors under what I consider to be the electronics part of the course. And now we're going to move on to our first integrated circuit, operational amplifiers. Okay, so op amps are, I think, really useful devices. If you have to amplify a voltage, make a voltage bigger, like multiply it by 10, let's say. Let's suppose it's a sensor signal, it's an audio signal, it's something like that that you have to amplify maybe to get into a data acquisition device from a low voltage sensor. Operational amplifiers are a great way to go. So maybe you have a temperature sensor, its voltage range is maybe only on the order of millivolts, and you need the span to be like 5 volts for a data acquisition device. This is a great way to do that. Okay. All right. So let's bring up the op amp portion. Operational amplifiers. So this is the schematic symbol of an operational amplifier. An op amp is an integrated circuit. It's a set of electronics like transistors and other devices that you could buy in discrete packages, but instead these are all integrated onto a semiconductor chip. So semiconductor chips start their life out as wafers. So you have a wafer, those wafers are cut up into die. By the time you see these in your breadboard circuits, those die are packaged and wire bonded to the terminals or to the leads of a plastic package like this. Okay, so this is what a typical 8-pin op amp dual inline pin package looks like. Op amps function as high gain differential amplifiers. We're going to talk about what that means in a minute. So they're amplifiers. They can be used as amplifiers. They can be used as devices that decide is one voltage higher than another, and that's called a comparator. We're going to talk about those. So they have multiple applications. But let's just talk about the basics here. This is the schematic symbol for an op amp. It's that triangle with the plus and the minus on the inside. On the left, we have the inputs. So these two terminals on the left are the inputs. On the right, that's the output. Okay. Going back to the inputs, the input that has the plus next to it has this name. It's called the non-inverting input. So you're going to hear me say non-inverting input versus the other terminal, the input with the minus sign next to it, is called the inverting input. And we'll see what those do in this class. And let's see here. Something funny coming up here. We give these variables in this class to these voltages. V1, we're going to call that voltage V1 the voltage of the non-inverting input. V2 in this class is the voltage at the inverting input. So those are node voltages of those pins, of those inputs. The output we're going to call V out. Okay, so those are 3 of the 5 terminals. These other 2 are power supply terminals. So the one labeled VCC, it's not always on the top, but the one labeled VCC sometimes is called the positive supply, and the one labeled VEE is the negative supply. Okay, so this is an amplifier. It has to be powered, and these are the power supply voltages for that. The positive supply is typically something like 5 volts, 12 volts, 15 volts, 28 volts, something like that. The negative supply is typically something like negative 15 volts, negative 5 volts, and it can actually be 0 volts too. We'll look at some examples and why you might choose the voltages for those supplies for certain situations. Okay. The inverting, let's see, someone asks, is the inverting input considered a negative V2? No. So the inverting input is not necessarily a negative voltage, and we'll see that. All right. Okay, so here is what an op amp does in one simple equation. An op amp does this. The output voltage of the op amp is this number, AOL, it's called the open loop gain, times V1 minus V2. Okay, the open loop gain is something typically big. It might be on the order of 10,000 or 100,000. I say a million, usually they're not that high, but somewhere in the thousands to 10,000s range. Okay, it's a big number. It's a gain. It's a number that you multiply by an input voltage to get an output voltage. Okay, here are the input voltages. So this op amp takes the difference between the input voltages, V1 minus V2, and it multiplies it by this big gain to give you V out. Okay, that's why, let me go back to the second bullet up here, this op amp functions as a high gain differential amplifier. High gain because AOL is a big number, 10,000, 100,000, and differential amplifier because you're taking the difference between two voltages and multiplying that by the gain. Okay. Okay. Let me mention also something. I see the other comment in the text. So I see plus minus associated with VEE and VCC, not V1 and V2. So yeah, this is a little confusing about the symbol. You on the left, you won't always see the non-inverting input at the top. You won't always see the inverting input at the bottom. Here's what you do know. The input next to the plus is always the non-inverting input. It is always what we call V1. So the input with the minus next to it is always the inverting input. It's always what we're going to call V2. Okay. Likewise, the positive supply can be drawn on the top or the bottom. The negative supply can be drawn on the top or the bottom. But if you see VCC written next to the terminal, it's always the positive supply. VCC is always the positive supply. VEE is always the negative supply. Okay. So you'll see some examples in homework of that. So pay attention. Where the plus and the minus are oriented next to the inputs and where VCC is written, VEE is written. Okay. Okay. So if you let VID, if I call this voltage VID, the voltage between the non-inverting input and the inverting input, VID comes from input differential voltage. Okay. If I define this as VID, then V out is AOL times VID because VID is just V1 minus V2. Okay. So that's what an op amp is. It's what an op amp does. And we're concerned with using this device, which has this characteristic, right? Or this characteristic over here. Using this device in useful ways. We're going to build amplifiers and we're going to make a circuit that compares voltages, like in a thermostat, for example. Okay, looking at a real example of an op amp, right here is the LM324 op amp. This is an 8-pin, 14-pin device. 8 pins, 14 pins, 7 on this side, 7 on the other side. Okay, and so wait a minute, why does this op amp have 14 pins when it's only a 5-terminal device? It's because this op amp chip actually has multiple op amps packaged into it. So you can see it has 4 op amps. So the LM324 has 1, 2, 3, 4 op amps. For each op amp, you have 2 inputs and an output, right? Instead of calling the non-inverting input V1, they call it input 1 plus. Instead of calling the inverting input V2, they call it input 1 minus. So you're going to see variants of this depending upon the manufacturer and the data sheet. But know that when you're looking at this symbol, the input with the plus next to it is the non-inverting input. The input with the minus next to it is the inverting input. And at the pointy part of the triangle, that's the output. Okay. Well, where are the power supply pins? Well, look here. So this chip, this data sheet, this is out of the data sheet, it calls VCC V plus. Okay. And it calls VEE ground. It's a little bit misleading because this ground, if you look in the data sheet, you could set this ground to a negative voltage. It doesn't have to be ground. It can be a negative voltage. And so that's why we're going to call this VEE. We're going to call this VCC. I'll be clear in my schematics when we talk about this, but you'll see data sheets with other variables used, other notation. Okay, so some people are bothered. Well, what's inside this triangle, right? Well, how do we know what this does? And why don't we just go make this out of transistors? Okay, so if you look inside of one of these symbols, the data sheet for the LM324 actually shows you, not exactly, but pretty close, what's in there. And this is what's in there. Okay, so you can see here are the inputs. Here's the non-inverting input. Here's the inverting input. Here's the output on the right. Okay. Up at the top, you have V plus, that's your VCC. It's because it's connected to the collectors here. And here's VEE at the bottom. All the ground symbols are VEE. They don't have to be ground, but that's how they show them here. And they're connected to the emitters of the input stage here. Okay, so that's what goes on inside. Now you could go build this. You could go figure out how to use these however many transistors and current sources and resistors and a capacitor and go do what they've done for you on an integrated circuit. But why do that, right? So this is available to you in a small package. And what does this do? It creates a high gain differential amplifier. So we're just going to look at this symbol. We're going to assume the manufacturer got it right, got these transistors right to give you an op amp with an open loop gain of something big like 10,000, and it's a differential amplifier that can operate over a certain voltage range. Okay, so but this is inside. You don't need to know this, but I wanted to show this to you. Okay. So when you see an op amp circuit, I'm going to give you this guidance on how to solve it. Okay. And tell you what we're going to do with these circuits in this class, and they're very common applications. So we will use op amps for two purposes, okay, in this class. We're going to create circuits that perform linear functions, or we're going to analyze circuits that perform linear functions. What are those linear functions? Function like an amplifier. You want to make a voltage bigger. Function like a filter. You want to make a low pass filter or a high pass filter, but unlike what you did in lab, you might want to build some gain or some amplification into the filter. Okay, or you may want to figure out what's a filter with a sharper roll off to the stop band from the pass band. You can build amplifiers called transimpedance amplifiers that convert a small current to a larger voltage so that you can detect small currents. Okay. So that's the first thing we're going to do with op amps, or analyze with op amps. The second thing we do is compare voltages. Those types of circuits are called comparators. Comparators compare two voltages. Okay. And so when you see an op amp circuit, this is the decision tree you should go through, right? This is what I recommend you go through. There's the first decision to make is, does the circuit have negative feedback? We're going to talk about what negative feedback is. It's easy to identify, but for now, let's just say you can identify negative feedback. If you have negative feedback, you have a linear op-amp circuit, that's number one up here. Okay, that's how you tell the difference between number one and number two. Number one has negative feedback. If you have a number one linear op-amp circuit, then if you've never seen the circuit before, you're going to use what we call the negative feedback approach. Okay, I'll show you how to do that. If you've seen the circuit before and you just know the answer, you know the gain of the amplifier, we're going to call that a common circuit. You already know the gain, you know the equation, so you don't need to do the negative feedback approach. Okay, and I'll show this decision tree a couple times, but so if you have an op-amp circuit and there's no negative feedback, now you are dealing with a comparator. Okay, that's number two up here. And we're going to look at two types of comparators. We're going to look at a simple comparator, just compares two voltages with a single threshold. And then we're going to look at a comparator with hysteresis. And that's a comparator with two different thresholds, and the threshold that the circuit pays attention to depends on the output state. Okay. All right. So let me bring you down the left-hand side of this tree. Okay, let's suppose we have an op-amp circuit and we want to identify negative feedback. Well, how do you identify negative feedback? So here's the op-amp. I've shown 3 of the 5 terminals. Oftentimes in a textbook problem, we don't show the power supply connections when you have a linear circuit because you just assume that the op-amp is sufficiently powered. Unless it matters, unless the power supply values matter, oftentimes we leave those off. We just say, yeah, this op-amp, it's powered, don't worry about it. It's powered with high enough voltages, we'll talk about that. The way you identify negative feedback, to go down the left side here, is you try to identify, is there some connection between the output of the op-amp and the inverting input, the one with the minus sign? If you have some path between the output of the op-amp and the op-amp's inverting input, assume that you have negative feedback. Okay, so this could be a resistor, a set of resistors. If it's a filter, it could have capacitors in there. But if there's some path you can identify between the output and the inverting input of the op-amp, assume you have negative feedback. Notice the asterisk I'm going to throw fine print in here. The reason this is negative feedback is because the output can in some way influence or change the voltage, affect the voltage at the inverting input. Okay, that means that this path cannot have a node somewhere in there that is held at a node voltage by a power supply or a ground connection. In other words, if the output changes and the inverting input voltage doesn't change, you don't have negative feedback. So if there's something in here that just keeps the left side here from changing voltage as the output voltage changes, then you don't have negative feedback. I'll point out some examples of that, but generally, if you have some connection between the output and the inverting input, you have negative feedback. And then that means you have a linear op-amp circuit, right? You've gone down the left side of this tree here. And if you don't know what the circuit is, if you haven't seen it before, then you're going to use this negative feedback approach. Okay, and this is the approach right here. So first, you're going to assume that the input differential voltage is 0. Right? If you have negative feedback, what happens is this input differential voltage might start out at something non-zero, but it's going to get really close to 0. It's not going to be exactly 0. It might be microvolts, maybe even a few millivolts, but it's going to be really small compared to all the other voltages in the circuit. Okay, so bottom line is when you have negative feedback, the voltage between the two input terminals goes to almost 0. Just assume 0 for now. Because of the op-amp's design, the way it's built, you're going to assume that the input currents, right, these two currents into the inputs are 0. Not because of negative feedback, but because op-amps typically have high impedance inputs, the ones we'll deal with. And then Number 3, step 3 of this, you analyze the circuit using KVL, KCL, Ohm's law, everything you're used to figure out whatever you're looking for. Okay. Okay, so if you have negative feedback, then and you don't know the circuit, you've never seen it before, you're going to use this 3-step negative feedback approach. And we will work an example of that next week. Not next week, spring break, the week after that. Next class is the exam. Okay? So we'll end this class right now. So don't forget, in closing, homework is due on Tuesday, tomorrow. Take a look at that due date, due time, the assignment. The exam will be on Wednesday. Check out that announcement that I sent out about that. The details are also on Canvas. Thanks for joining class. If you want to talk about anything, just stick around for office hours. If not, I'll see you next time. Have a great night.